Very warm welcome to all of you. Today we'll be learning about the system of coupled oscillators, how they function, how they work, and the mechanism. We'll derive the conditions for the equations, the Q1 mode, the Q2 mode, and the normal frequency of oscillations of the coupled oscillator system. Right. So when we derive something, it is very important that we have the basics clear. So this is basically a system that we take. Say this is the support system. This is a pendulum A. This is a pendulum B, and they're both connected by a spring of constant K, and they're of equal length. The length of the pendulum is equal for both cases, and they're of equal mass as well. These are the fundamental assumptions that we will make in our journey to finding the equations for a coupled oscillator system. Now we will see what happens when they're stretched. So you can see that they're clearly dependent on each other because they're connected by the string, right? So in a more magnified way, uh, we can show it like when you pull it. Say this is your y1, this is your L. Let this alpha angle be alpha. This is your mg, and similarly this is your pendulum B. When stretched like this, let it be displaced by y2. Now this is the weight mg acting downward, vertically downward, and let this be L as we had assumed earlier, and let this angle be beta. And of course there is a spring that is joining the two bodies. So we will now find out what are the forces acting on these bodies. So what are the forces that are acting on these bodies? Let's say for body A. For body A, what are the forces acting on the bob? So when it at this position, it has a restoring force F is equal to minus mg sine alpha. Now in this particular case, what is sine alpha? Sine alpha is nothing but your y1 divided by L. So we can substitute minus mg y1 by L, and also you have the force due to the, because it has extended, there's a force because of the spring. Another force is your minus k, where k is the spring constant of the connected spring. We can write the change as y1 minus y2, right? So we can write that y1 minus y2. Similarly for your body number B, you have the same kind of forces, just that the angles are opposite, minus mg sine beta, which gives you minus mg y2 by L, right? And you have f is equal to minus k. In case of b, it will be y2 minus y1 corresponding. Right, so we have got the forces. So what force balances these forces for both the cases? This one for body A case and this one for B case. What is that force? There is nothing but your inertial force that balances these two forces acting individually on the two bodies. Right. So how can we uh, denote the equation of motion? Let's say for body A. For body A, we can write the differential equation as d square say y1 by dt square times m, which is the inertial force, that is equal to minus k of y1 minus y2 minus mg y1 by L, right? Or you can write d square y1 by dt square is equal to minus k by m times your y1 minus y2. We are dividing both sides by your m, minus g by L to y1. So we can write this finally as d square y1 by dt square is equal to minus k by m times y1 minus y2 minus omega square y1. As we know, omega is equal to root under g by L. So let this be your equation number 1. Now for your body B, what are the forces? Similarly, we can write m d square y2 by dt square is equal to minus k to y1 minus y2 minus y1 minus mg y2 by L. So dividing m on both sides, we get d square y2 by dt square is equal to minus k by m times y2 minus y1 minus g by L times y2, which is nothing but d square y2 by dt square is equal to minus k by m of y2 minus y1 minus omega square y2, whereas in the previous case omega is equal to root under of g by L. So we have got the equation of motion, and let this be equation number 2. Now we will add. So equation 1 plus your equation number 2 gives you d square y1 plus y2 by your dt square is equal to minus k by m y1 minus y2 plus y2 minus y1 minus omega square y1 plus y2. But here y1 cancels out, y2 cancels out, so we can write d squared of y1 plus y2 whole by dt squared plus omega squared y1 plus y2 is equal to 0. Now let y1 plus y2 be Q1. Therefore, d square Q1 by dt squared plus omega squared times Q1 is equal to 0. This is your one of the equations for your coupled oscillating system. This is called the Q1 mode, but we will come to this later. So also now equation 1 minus equation 2 gives us d squared of y minus y1 minus y2 by dt square is equal to minus k by m y1 minus y2 minus y2 plus y1 minus uh, omega squared of y1 minus y2. So we can find that d squared y1 minus y2 by your dt squared is equal to minus 2k by m y1 minus y2 minus omega squared y1 minus y2. We can find this, right? So we will transfer this and we'll assume, let y1 minus y2 be q2. So we can write d square q2 by dt squared plus taking the q2 common and on transferring it to the left hand side, find that 2k by m plus omega square is equal to 0. Now we assume quantity called omega 1 squared to be equal to 2k by m plus omega squared. Therefore, we can write the final equation of motion for body number B to be d squared q2 by dt squared plus omega 1 squared q2 is equal to 0. This is your second equation of motion for the coupled system. So these are the two equations. This was the first equation and this is your second equation. So we've got the two modes, Q1 and Q2 modes. We'll discuss what the modes are. So when we talk of Q1 mode, what is this Q1 mode exactly? So in Q1 mode, your Q2 will always be equal to 0. This is the essential condition of Q1 mode, right? So if it is 0, we know Q2 is what? Q2 is y1 minus y2. Therefore 0 equal to y1 minus y2, or your y1 is equal to y2, which means the system moves with, say, equal displacements. Say this is y1, so this will also be y1, right? And always it is in phase. So the amplitude, the frequency, and all, so on, associated parameters remain same. And this mode is also called your in phase system. In phase system. Why? Because these two bodies are always in the same phase. They always go together. Whatever they are, they go together. And we have the last condition for your Q2 mode So similarly, in Q2 mode only Q2 exists and Q1 is equal to 0, which is your fundamental condition. Therefore, we can write y1 plus y2 is equal to 0, or we can say y1 equal to minus y2. So in this particular case, we find that the displacements are equal, but it is in opposite direction. Both are in opposite direction. Therefore, if they are to be in opposite direction, say this is the body we are considering, this is the pendulum A, then this will be the pendulum B, and let's say that this one is y1, this one will also be y1, but look, the directions are apart. Pendulum A is being towards this direction, pendulum B is pulled towards this direction, so it is going to be in opposite directions. So this system is also called your out of phase system. This system is also called the out of phase system. Why? Because you have the two pendulums always moving opposite to each other. Y1 is equal to minus y2. So you're mostly done with this concept of coupled oscillator. Mostly done. We just have the last portion, which is nothing but the two modes. So you have your mode of lower frequency, what is this? Mode of lower frequency is nothing but omega. Omega is equal to root under of G by L, or frequency is 1 by 2 pi G by L. Why? Because your frequencies F is equal to omega by 2 pi, and we have the mode of higher frequency, which is your omega 1 mode. Omega 1 is the square root of 2k by m plus G by L. So the corresponding frequency is 1 by 2 pi root under of 2k by m plus G by L. So this is your mode of higher frequency, and this is your mode of lower frequency, this, right? So that is all for the concept of coupled oscillator. So if you have any doubt, you can leave that in the comment box below. I'll definitely try my best to respond as quick as is possible, and thank you for watching. It's a pleasure to have taught you. Have a good day ahead, and do hit the subscribe button. Thank you.